And then he was like, no.
All right, good day, everyone. So if you can settle down, then we can start our lecture for today on reversibility. Essentially still talking about heat engines, but this time we're talking about the perfect or reversible heat engine. So just a reminder of what we've been talking about. Yesterday, we learned about the heat engine, which is a consequence of the second law of thermodynamics, whereby energy flows spontaneously from a hot temperature source to a cold temperature sink. And in the process of heat transfer from hot to cold, work is done. And so essentially every heat engine draws energy from a hot source, does work, and expels out some heat waste to a cold sink. And yesterday we learned how to calculate the efficiency of the heat engine, efficiency being defined as output over input. The output of the heat engine is the work that it does, and the input is the energy that it draws from the hot source or hot reservoir. And so the efficiency is work over the energy acquired from the hot, which is the subscript H reservoir. And then we use the conservation of energy, which says that whatever energy is input into the heat engine, meaning QH, should total the energy going out of the heat engine, which is the work done and the heat waste. And so you have this relationship. The input energy from the hot reservoir is equal to the work plus the heat waste to the cold sink. We can rearrange this to have an equation for the work that's done, and therefore we can replace this expression of work in terms of the energies, QH energy from the hot reservoir and QL energy to the cold sink, and we have an efficiency just in terms of the energies of the cold sink and hot reservoir. And from there, from this form of the efficiency, we deduce that we cannot have a heat engine that's 100% efficient, meaning every device will always have a heat waste, and that's a consequence of the second law of thermodynamics. So the engine that we talked about is a real engine. There are frictional losses, and because there are frictional losses, you cannot just collect the total energies in the output and the heat waste adding up to the input. There are frictional losses somewhere here in the work done. Also, there could be some frictional losses as energy flows from the hot reservoir to the cold sink. And because there are frictional losses, we cannot plot the pressure and volume diagram or PV diagram of this heat engine. We know in reality, there's always frictional losses, so we call this engine a real engine as well. If there are no frictional losses, say assuming that there is an engine that's frictionless, so that the frictional losses is zero, we know that this is not possible in reality, right? Because in reality, there will always be friction. But although it's not possible to have a real or an ideal engine where there is no frictional loss, the concept of a perfect or an ideal engine is important theoretically. And so we will look at that in this lecture. And it's important theoretically because it allows us to plot a pressure volume diagram or a PV diagram. And from the PV diagram, we will be able to derive one more equation that tells us about the efficiency of an engine. Right, for an idealized or perfect engine where there is no frictional losses, the cycle is reversible. When we say reversible, we mean that the processes that can be done in reverse in exactly the same manner where the magnitude of work and heat exchange, so that's Q and QL and QH, they're all equal throughout the processes, regardless of the direction that you take. So for example, this is an illustration of a reversible cycle. Say you have an ideal gas that starts at state 1. Okay, it's compressed isothermally to state 2, and then its pressure decreased isovolumetrically, and then it is expanded isobarically back to state 1. If you calculate the work done in going from state 1 to state 2, state 2 to state 3, and state 3 back to state 1, in an ideal or perfect engine, it doesn't matter in which direction you calculate the total work done. Okay, if you calculate the total work done in reverse process, such that the ideal gas undergoes an isobaric compression first, followed by an increase of pressure isovolumetrically, and then isothermal expansion back to its original state, the magnitude of the work done calculated using different paths should be equal. Okay. But if you recall, we already learned when we learned about these PV diagrams and the first law of thermodynamics, right? We had an example where we said that the work done is dependent on the path. It depends on whether your gas goes actually through this isothermal process first or through this isobaric process first. So we already saw in our lecture, First Law of Thermodynamics, that this cannot happen in reality. So this is an ideal engine. So this reversible process in a reversible engine is ideal, is perfect, because it does not really occur in real life. But as I said, it's important conceptually. So let's look at an example of an ideal engine, or an example of a perfect engine. An example of a perfect engine is called the Carnot engine. Okay, it's not real. There's no real Carnot engine in real life. It's just an idealized engine that was conceptualized. So it's just in the mind of the French engineer Carnot. So he idealized this engine by saying that what if you have a perfect engine that can undergo a frictionless reversible cycle? What concepts can we derive from this perfect engine? Okay. And so this engine was named after him because he was the one who dreamt about it or conceptualized about it. And his concept was like this. So the Carnot engine, it's still a heat engine. So it still requires a hot reservoir where the engine draws heat from. Okay, so you have
All standard.
You have a hot reservoir. The engine draws heat from the hot reservoir. As a result of heat being drawn, the gas in the piston expands. The gas expands isothermally. You have this isothermal expansion of the gas. Okay, when the hot reservoir is taken out, the gas has momentum in its expansion. So the gas still continues to expand, but it expands adiabatically. Okay. Then the gas, once it has expanded to its full volume, the gas still needs to expel some energy to a cold sink, right? So you have this cold sink and you have heat being expelled. As heat is expelled, the gas contracts or compresses isothermally. Okay? So you see this isothermal compression of the gas here. When the cold sink is taken out, the gas again has momentum in its compression. So the gas continues to compress, but this time compresses adiabatically until it reaches the original state, in which case the cycle repeats itself. You have this isothermal expansion because of energy input, followed by adiabatic expansion as the momentum of the gas allows it to expand continuously, followed by this isothermal compression as heat is expelled to the cold sink, followed by this adiabatic compression as the gas maintains its momentum during its compression. All right, so the idealized Carnot cycle still is a heat engine, still requires a hot reservoir where the engine draws energy from, allowing it to have this isothermal expansion. So that's the first process. Then the adiabatic expansion. Okay, the Carnot engine still has a cold sink, right, which allows the gas to compress isothermally. That's the third process. And finally, compress adiabatically. So 4 processes involved in the Carnot cycle. But what we can notice is that the processes involved, isothermal and adiabatic, they mostly involve temperatures, right? Isothermal processes, constant temperature, and then adiabatic processes, they go from one temperature to another. They go from one isotherm to another. So the idealized or Carnot cycle in an idealized or Carnot engine involves isothermal and adiabatic processes. And because they're temperature dependent, we can then define the efficiency of the Carnot engine in terms of absolute temperatures. Right. Right, so compare this to the efficiency of the real engine that we saw yesterday. Right, so for the efficiency of the real engine or the irreversible engine that we saw yesterday, the efficiency is calculated from the energies expelled as heat waste to the cold temperature or low. So this is cold sink energy to the cold sink, energy expelled as waste to the cold sink divided by the energy drawn from the hot reservoir. For the Carnot or ideal engine, what we need are the temperatures. It's the temperature of the cold sink. So this is temperature of cold sink, and the subscript L tells you low temperature, and the subscript H tells you hot reservoir. So that's the temperature of the hot reservoir. So if you want to calculate the efficiency of a perfect engine, an ideal perfect or Carnot engine, then you only need to consider the temperatures. But then you have an idea of what the efficiency of your engine is, the maximum efficiency of your engine is. Then you build your real engine, and when you build your real engine, you calculate its real efficiency using how much energy it actually draws from the hot reservoir and how much energy it actually expels through the cold sink. All right. Okay, so you see the difference between these two efficiencies, and we'll talk more about that. We'll practice more about the differences of these two efficiencies. But as I said, this idealized efficiency conceptualized by Carnot has important implications, because if you look at this equation here, when will you have 100% ideal efficiency? It's when TL, the temperature of the cold sink, is equal to 0, isn't it? Right? So if you are able to achieve 0 kelvins, remember we're talking about absolute temperature in kelvins. If you're able to achieve 0 Kelvin temperature, then you will have an engine with 100% efficiency. if you can have a cold sink that is maintained at 0 Kelvin. However, 0 Kelvin is actually impossible to achieve. Well, not yet, not to date. So to date, the world record for the lowest temperature achieved in a lab is 38 picokelvins. Pico is times 10 to the minus 12. So this is trillions. So this is 38 trillionth of a Kelvin. So it's still, it's very, very low, okay, but it's not zero. Right, so it's not zero, so it's still up to date. It's still impossible to have zero efficiency, and they achieved this. It's a very low temperature, but they achieved it only for 2 seconds, and then they went back to room temperature. So it's, yeah, so it's still not possible to have a 100% efficient ideal engine, and in fact, it's very, very difficult to achieve very, very low temperatures that it deserves its own law. So the third law of thermodynamics says that it's impossible to have 0 Kelvins. Okay. Until that day when scientists are able to break the world record and they can actually achieve 0 Kelvin, the third law of thermodynamics still stands, and we cannot have 0 Kelvin. And that has important implications for our electronic gadgets and devices, because then the Carnot efficiency gives us the maximum possible efficiency that an engine can have. If you want to build an engine, like a car engine or a refrigerator, fridge, heat pump, or whatever engine, if you want to build an engine, you can first estimate how much maximum efficiency you can have by thinking about what's the lowest temperature sink that you can achieve and what's the highest temperature reservoir that you can make without, of course, without melting your iron or whatever materials you're using to build the engine. Once you've determined what the lowest temperature and highest temperature you can have in your engine, you can then estimate what's the maximum possible efficiency that you can have, assuming that you don't have frictional losses, right? That will be the maximum possible efficiency in your perfect engine. Okay. But then the real engine that you build will always have frictional losses. So the real engine you build will have an efficiency that will be less than the perfect or Carnot efficiency that you've estimated, right? And in reality, well-designed engines, real engines, reach about 60 to 80% of the Carnot efficiency. Right. Right, so still our electronic devices, they're not highly efficient still, because firstly, you cannot achieve 0 Kelvin. So you cannot in the first instance have 100% efficiency for your perfect engine, and therefore having 80% real efficiency is not achieved. What's more realistic is probably somewhere like 80% or 80% efficiency in a perfect engine, and then take into account frictional losses, and that will give you 60 to 80% of that 80%. You know what I mean? Okay, right. So that all tie up together. So the Carnot efficiency or ideal efficiency gives you what efficiency you can have if you had a perfect engine without frictional losses. And then the real, right? So compare that to the real efficiency is how much efficiency you can actually have if you built a real engine, and taking into account the heat waste and how much heat you can get from your hot reservoir. Okay, good. Let's look at some examples to compare the two kinds of engines, Carnot or perfect engine and irreversible or real engine. So here you have an engine. It's hot. So its hot reservoir TH is maintained at 600 Kelvin, and there's a cold sink TC that's maintained at 270 Kelvin. This engine draws 8,000 joules of energy from the hot reservoir. As a result of heat flowing from the hot reservoir to the cold reservoir, some work is done. The heat waste is 4,000 joules to the cold sink. Is this a reversible or a perfect or a Carnot heat engine, or is it an irreversible heat engine, or is it a hoax, an impossible engine, or none of the above? I don't know what none of the above means. It's just either of the three, actually. Any wild guesses? Yeah, it is number two. It is a reversible engine. So how do we determine between Carnot or reversible engine? So Carnot's engine, this is your ideal perfect engine, right? So you can calculate first your Carnot efficiency using the temperatures of the reservoir and the sink. Okay. Yeah, your temperatures are already in Kelvin, so that's all good. Temperature of the cold is 270 divided by temperature of the hot. Take that away from 1, giving you an efficiency of 0.55 or 55%. So this is the maximum efficiency that you can have, right? Assuming that your engine's perfect. But this engine draws 8,000 joules and expels 4,000 joules. So if you calculate the real efficiency, you then have QL, the energy expelled to the cold sink, divided by QH, the energy taken from the hot reservoir. Take that away from 1, you calculate a real efficiency of 0.5 or 50%, which is smaller than the perfect efficiency that a Carnot engine gives. And therefore, this engine can exist in real life. Right, it's a irreversible or real engine. Cool. All right, next question. Is this we have this engine. It's a Carnot engine. Is this, what's the efficiency of this Carnot engine? Okay, so you have the hot reservoir here, cold sink. You're given the temperatures. Heat flows spontaneously from hot to cold, and therefore doing work in the process of heat transfer. But what's the efficiency of this Carnot engine? So Carnot's efficiency uses temperatures, okay? Right, and hence you don't need QH, QL, or W. You're given the temperatures. Okay, it's easy to be fooled by Celsius temperatures, and you can probably think that the efficiency is 0.5 because that's 200 divided by 400 is 1/2. 1 minus 1/2 is 0.5. But the really important thing to remember is that temperatures are absolute temperatures. They must be in kelvins. All right, so you have to convert your temperatures by adding 273 and use the Kelvin temperatures to calculate the Carnot efficiency or perfect efficiency. Right. So it's less than 0.5, specifically it's 0.3. Good, right? Okay, last chance to test our understanding. You're given the heat engine. Again, you're given the temperatures, hot reservoir and cold sink. Okay, they're given in kelvins, right? So nothing tricky now in terms of temperatures, and you're given how much heat is drawn from the hot, so that's QH, heat drawn from the hot reservoir, and you're given how much heat waste is expelled to the cold sink. Okay. Do you think this engine is a perfect reversible Carnot engine, an irreversible real engine, or an impossible engine? Okay, right. It can be any of the three, right? Let's look at how we do this. So irreversible engine, you can determine whether it's irreversible if you calculate the efficiency, and that efficiency is less than the Carnot engine, right? Like what we did in the first example. If it's a Carnot engine, if it's a Carnot engine or reversible engine, if E ideal or E Carnot is equal to E real, meaning if the efficiency you calculate from 1 minus QL over QH is equal to the efficiency you calculate from 1 minus TL over TH, if they're equal, then that's a reversible Carnot engine, because that means you're able to build the engine perfectly. The real efficiency you get is equal to the perfect, the ideal efficiency of the perfect engine. It's an irreversible engine if the ideal efficiency you get is greater than the real efficiency that you get, because of frictional losses, the actual efficiency of the real engine will be less than the efficiency of the perfect engine. So this is how you determine whether it's an irreversible engine. And it's an impossible engine if the ideal efficiency is less than the real efficiency, right? Because the ideal efficiency, this is the efficiency of a perfect engine. And you cannot have any efficiency more than perfect, right? You cannot have more perfect than perfect. Okay. Right? If the efficiency of the perfect engine is 80%, you cannot build a real engine whose efficiency is more perfect than 80%. Yeah. So that's how you determine an impossible engine. So determining the answer requires you to calculate the ideal efficiencies and the real efficiencies and compare those two, right? So let's do that. So Carnot efficiency uses temperatures. Okay, temperature of the cold, 300 divided by temperature of the hot, 600, and then take that away from 1, gives you a real efficiency of 0.5. And then for the real efficiency, use the energies, QL and QH. So QL, heat waste, 2000 joules, divided by QH, the heat drawn from the hot reservoir, 8000 joules. Okay, divide those two, take that away from 1, gives you an efficiency of 0.75 or 75%. And you cannot build anything more perfect than the Carnot or the ideal engine, and hence you cannot have 75% efficiency if the perfect engine can only have 50% efficiency. So what we have been learning so far is that heat will flow spontaneously from hot to cold, and as a consequence, thermal energy is converted to mechanical energy, and that's exactly how the heat engine works. And we have looked at the real or irreversible engine and the ideal or Carnot engine. But if it's true that heat can flow spontaneously from a hot object to a cold object, then it should also be true that heat will not flow spontaneously from a cold object to a hot object. Meaning that if we wanted heat to transfer from this cold sink to the hot reservoir, then heat cannot spontaneously transfer by itself. Instead, work needs to be done in order to facilitate the heat transfer from cold to hot objects. So in this case, we need work input. So this slide just summarizes the difference between the heat engine and the refrigerator or air conditioner, which is what we learned in the previous slide, where heat will not flow spontaneously from cold to hot. So in the heat engine, heat or energy will flow spontaneously from the high temperature reservoir to the low temperature sink. And as a result, work is done in the heat engine, and that is the work output. On the other hand, for the refrigerator or air conditioner, we want to transfer heat from the cool environment of the refrigerator in order to maintain the low temperature of the inside of the refrigerator. And when we transfer energy from cold to hot, the second law of thermodynamics says that this cannot happen spontaneously, but instead work needs to be input in order to facilitate heat transfer from cold to hot. So notice the difference in the arrow, the change in the direction of the arrows in the heat engine and the refrigerator or air conditioner. So the implication of the second law of thermodynamics, where heat will not flow spontaneously from cold to hot object, is that first, work needs to be done in order to facilitate the flow of heat from cold to hot. And the second implication is that a perfect refrigerator where work does not have to be done does not exist, which means that every refrigerator needs a pump. And we need to plug the refrigerator into an electrical outlet for the pump to work. And the pump facilitates the transfer of energy from the cold refrigerator to the warm outside environment. And we learned that if the refrigerator loses energy, then the temperature decreases, and therefore the inside of the temperature is maintained at a lower temperature, and it's kept cool. So we can also define something similar to efficiency. Like when we were talking about heat engines, we defined efficiency as the output over input. And this is a general definition for efficiency, except for the heat engine, the output is the work done and the input is QH, the heat from the hot reservoir. Now for a refrigerator, instead of defining efficiency, we define the coefficient of performance of the refrigerator. And the coefficient of performance can be defined in the similar way as efficiency. It is output divided by input. So if we have to think about the objective for the refrigerator, what do we want to achieve for the refrigerator and or air conditioner? Well, we want to achieve a cold inside of the fridge or a cold room, and therefore we use an air conditioner. And to maintain a cold inside of the fridge, we need to remove energy from the cold inside and put that into the outside warmer environment, and therefore we need to input work. So in other words, the output, which is what we want to achieve, is the cold temperature inside the fridge, and the input is what we need to do in order to achieve that output, and the input is to do work in order to facilitate energy transfer from cold to hot regions. So the coefficient of performance is defined as the output which is the heat removed from inside the refrigerator divided by the input, which is what we want to do in order to achieve the output, and that is the work done to remove the heat. So we can write that if the output is QL and the input is W, then that's QL over W. But also energy still needs to be conserved. So you have, if you notice the direction of the arrows here, QH should be equal to QL plus W. Right? Whatever goes into the refrigerator should be the same amount of energy going out of the refrigerator. And therefore, if we rearrange this equation, we can write work is equal to QH minus QL. Hence, we can substitute work here is equal to QH minus QL, and we have the coefficient of performance in the form of QL and QH. For an ideal refrigerator, just like we did for the ideal or Carnot's engine, instead of using the energies Q, we use the temperatures TL. So TL is the temperature of the cold temperature inside the refrigerator. So this is cold temperature inside the refrigerator, and TH is the hot temperature outside of the refrigerator. In a similar way, we can also define heat pumps. So heat pump also uses the concept where we want energy to flow from the cold outside to the warm inside. Right? We use heat pump to keep the inside of the room warm. And the way to keep an object warm is to heat it up, meaning the object needs to gain energy. All right, so you need heat flow going into the warm room. And where will the heat come from? The heat will come from the cold outside, right? So the cold outside will lose energy, and that lost energy is gained by the warm room. Again, second law of thermodynamics says that this cannot happen spontaneously. Heat cannot flow spontaneously from the cold outside to the warm room, and hence you need a pump to do work in order to facilitate the energy transfer from the cold outside to the warm room. So similarly, we can, so look at the objective for the heat pump is to heat up the room rather than cool it down as opposed to the refrigerator. So the output we want is the warm room, QH, and the input is the work that's done by the motor that will move the energy from the cold inside to the warm cold outside to the warm inside. So we can again define the coefficient of performance to be the desired output. Our desired output is the heat, is to heat up the inside of the house. So heat delivered inside the room, which is QH, divided by the input, and that is the work that the pump needs to do in order to facilitate heat transfer from the cold outside to the warm inside. So output is QH and input is work. Again, we can write down the conservation of energy. Looking at the arrows here, we can see that QL should be equal to QH plus W, or in other words, W is equal to QH minus QL. So this is again for a real heat pump. For an ideal or Carnot heat pump, we can again write down the coefficient of performance in terms of the temperatures instead of in terms of the energy. So instead of using QH and QL, you use TH and TL. All right, let's do a quick check here. So Right, so here you're given a refrigerator and you want to find the coefficient of performance of this refrigerator. So in this case, it's a refrigerator because the direction of the arrow shows you that energy comes from the cold region and it goes to the hot region. So you have this flow from cold and energy flow from cold to hot. And second law of thermodynamics says that work needs to be input in order to facilitate the heat flow from cold to hot. Right, so coefficient of performance is output over input. It's a refrigerator. What we want is to maintain a cold inside of the fridge, and so the output will be 60 joules and the input will be the work that's done in order to facilitate the heat transfer from cold to hot. And so the input is the work done, 40 joules. That gives you a COP. Sorry, this is a COP of 1.5. Okay. Now, what if it was a heat pump instead of a refrigerator? So if it were a heat pump instead of a refrigerator, so we want to maintain a hot temperature for the heat pump, and to do that, heat needs to go from cold temperature to hot temperature again, but you need work in order to facilitate heat flow from cold to hot. But this time the output is the warm room instead of the cold inside of the fridge. So COP will be 100 joules because you want to maintain a hot, warm room for the heat pump, and the input is still the work done in order to facilitate energy transfer from cold to hot. That gives you a COP of 2.5. All right, so this ends our lecture on the second law of thermodynamics and heat engines, as well as refrigerators and heat pumps.